Okay, this lesson is on the power rule. Our learning goals for today are learning to use rules to find the derivative or differentiate functions of the form y equals a x to the n. We're learning to apply the power rule to differentiate polynomial functions and functions containing rational, so fraction, and negative exponents. We're learning to apply the power rule to find the slope of the tangent to a function at a specific point, and we're learning the different notations for the derivative, i.e. the slope of the tangent at a general point. Mathematicians were able to generalize rules for finding the derivative. The first one, the easiest one to generalize, was the constant function rule. Makes sense from a graphical point of view. So let's say this is the x-axis and this is the y-axis, and we have some function f at x equals some constant k. We know it's going to be a horizontal line somewhere. Okay, and we could see that the slope of the tangent is going to be 0 because the slope of the line is 0. Okay, and it's 0 everywhere. So it makes sense from a graphical standpoint, but we can also prove it using our first principles. So our derivative formula is f prime at x is the limit as h approaches 0 of f at x plus h minus f at x over h. And we know, since this is our defining function, that it doesn't matter what we put in for x, we're always going to get out k. Doesn't matter. Okay? So f at x plus h is k, f at x is also k, some constant. So when we sub those in, we're going to get k minus k over h, which is going to show us that f prime at x is, here's our 0 pair. So we just have 0 in the numerator, so the derivative is 0. Okay? Which makes sense, because if we have a, graphical point of view, but here's an example then. So for instance, if we had a function f at x equals -5, without having to do a proof, just knowing, we know that the derivative is going to be 0. Okay, so the slope of the tangent to that function is 0 everywhere. We know it. It's a rule now. We don't have to prove it every time using first principles again. The next important one is the power rule. And it says that if f at x is x to the power of n, where n is a constant, then f prime at x is n times x to the n minus 1. So it's saying if we have a power function like this, x to the n, then the derivative is going to be n, so the n from the exponent drops down in front, and we still have x, and then the exponent reduces by 1. Pretty great result. It will really help us to differentiate polynomial functions, but we have to prove it first. So we start off with our derivative formula. And this is our defining function for f at x. So if we had f at x plus h, it would be x plus h to the power of n. And we know f at x is x to the n, so we could fill those in. So f at x plus h is x plus h to the power of n minus f at x is x to the n all over h. Okay, so we want to find a way to deal with the numerator here, and in order to do that, I'm just going to go away for a second and remind you of something we learned in grade 11, which is going to help us here. So in grade 11, we learned something called Pascal's triangle, and we used it to help us expand powers of binomials. And Pascal's triangle was like 1, 1, 1, 1, 2, 1, 1, and then you add those two, so it's self-propagating, etc., and then 5, 10, 10, 5, 1, and we could keep going and going, but we're not going to. I'm going to remind you that then how we would have expanded something that looked like x plus h to the 4th. So this is row 1, row 2, row 3, row 0, row 1, row 2, row 3, row 4, and row 5. And they name them that way because the second number in from row 0 is a 0 that you don't see. Second number in from row 1 is a 1. Second number in on row 2 is a 2. Second number in on row 3 is a 3. Second number in on row 4 is a 4. Second number in on row 5 is a 5. Okay? All right, and if you remember, so we would choose the fourth row of Pascal's triangle in order to expand something of the form x plus h to the fourth. The first term, we would take the first number in Pascal's triangle, which is a 1, so then you don't really need to show the 1, and it would be x to the fourth, h to the 0, which is also 1. And then the second term, take the second number in the fourth row of Pascal's triangle, and that becomes our coefficient, so 4x, reduce the exponent on x by 1, and increase the exponent on h by 1. So h goes from an exponent of 0 to an exponent of 1. Then we use the next number in Pascal's triangle. Exponent on x reduces by 1, exponent on h increases by 1. Next, so it would be 4x to the 1, h cubed, and finally a 1 h to the fourth. So that's how we could expand it out without using FOIL 3 times. And that, which would be a lot more labor intensive. So that's why we use Pascal's triangle, is so then now we can do the proof of the power rule. So if we come back here, so some things we can notice then is that the first term in the expansion was x to the fourth when we did the fourth row, so it's going to be x to the nth when we talk about the nth row. And we also know that the coefficient of the second number in is always, for row 4 it's a 4, for row 5 it's a 5, for row 6 it's 6. So for row n it's going to be an n. The coefficient of the second term is going to be an n. And then we're going to reduce the exponent on x by 1 and increase the exponent on h by 1. So h, here we would have had an h to the 0, we didn't need to show. Here we have an h to the 1. Third number in the nth row of Pascal's triangle we don't know, so I'm just going to use a capital C, doesn't matter. And the exponent on x will be reduced by 1, the exponent on h will increase by 1. And then same with the fourth number in Pascal's triangle for the nth row, we don't know, so I'll call it a d, x to the n minus 3 h cubed plus dot 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 plus the very last one in the nth row of Pascal's triangle, there's going to be a 1 coefficient, x to the 0, which we don't need to show, h to the n. So that all here represents x plus h to the power of n. And then we're subtracting x to the n and dividing by h. So we can see this 0 pair right here. We have x to the n minus x to the n. They're gone. And then also you can see that everything left in the top row contains, the term contains an h. That should be times h squared, my bad. So every term contains an h right to the end that's remaining up there. So we can common factor out that h. So h times, so if we common factor out h here, we're just left with nx to the n minus 1. Common factor out an h from the second term, we'd have cx to the n minus 2h plus dx to the n minus 3h squared plus dot 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 plus h to the n minus 1 all over h. And now we can divide out these h's. So now the denominator becomes a 1, and it's safe to let h approach 0. So if we let h approach 0, this term's going to approach 0, this term's going to approach 0, all the ones in the middle that have an h are going to approach 0, that one's going to approach 0, and the only term left is going to be the nx to the n minus 1. So we've just shown that f prime at x is in fact equal to nx to the n minus 1, which is important, really important, because it allows us to find the derivative of something such as f at x equals x cubed. We would automatically know that f prime at x, following this power rule, would be 3, so the exponent comes down, x to the 3 minus 1, which is 2. So again, now this is a rule we just know and can use rather than having to go from first principles every time, which is pretty powerful and pretty great. So we're going to go on. Okay, so I have some examples for us to work on. So the first one just says find f prime at x if f at x is x squared. So it's in a power function form. We have x to some exponent. So we should just be able to apply the power rule and say f prime at x is 2x to the 2 minus 1, which is a 1, which you would not need to show. So it would have been just as easy to just write f prime at x equals 2x. So when f at x is x squared, f prime at x is 2x. Okay, so that means the derivative anywhere, or the slope of the tangent anywhere, can be found using the formula 2x if the function is x squared. All right, so we did talk that we were going to find new notations. This means the derivative of y with respect to x. This is called Leibniz notation. And he was a mathematician who came up with calculus simultaneously at the same time that Newton did, only they were in different countries, so they weren't aware of each other at the time. So his notation is different. He doesn't use f prime at x, he uses dy by dx, which stands for the derivative of y with respect to x. So if they want us to use Leibniz notation, we still have y equals x to the 5th at our beginning, but then we're going to say the derivative of y with respect to x is 5, so the exponent comes down, x to the 5 minus 1, which is 4, so 5x to the 4th. And again, that's a formula to find the slope of the tangent anywhere to the curve y equals x to the 5th. Next one, if g at x is 1 over x cubed, then find g prime at 2. So the problem with this one is it doesn't have the setup of a power function, f at x equals x to some exponent. But we can use some of our exponent rule knowledge to rewrite it so it does look like a power function, x to the something. So 1 over x cubed, you guys should remember, we could also write it as g at x is x to the negative 3. Okay? So then we're going to want to find g prime at x. So again, using the power rule, it's going to be negative 3x to the, so we're going to subtract 1 from the exponent, negative 4. And then if we don't want to have a negative exponent, which you usually will not be allowed to have, we would write this as negative 3 over x to the 4th. Okay, so remember the negative 3 has an exponent of 1. It's fine in the numerator. X to the negative 4, we can move it to the denominator and the exponent becomes positive. But they're also asking us to find g prime at 2. So g prime at 2 would be negative 3 over 2 to the 4th, which would be negative 3/16. So that would mean the slope of the tangent to the curve 1 over x cubed at 2 would be negative 3/16. Okay, so if y equals the square root of x, then find y prime. Similar, okay, so y prime, that's another notation you can use. That also means slope of the tangent at any point. So we've seen prime, we already knew that one. Leibniz notation, dy by dx up here. And now we have just plain y prime, which we use a lot in differential equations if you get up higher in calculus when you go to university. So again, this one's really easy to write down. We have y equals root x, but that's not in the form of a power function again. But we can use our knowledge of exponent rules to write it as x to the something. So hopefully you remember that the square root of x is the same as x to the power of 1/2. And then y prime, okay, if we take the derivative now, is going to be 1/2 x to the 1/2 minus 1. And I'll do it out long this time. So you'd have to get a common denominator here to subtract 1. And usually you don't want to write your answer with a negative exponent. So the 1's fine where it is. It would be 1 over 2 root x. Put it back in radical form. Exponent's positive, and that's the prettiest way that you could write that derivative there. Okay, if f at x is 7, then find f prime at x. So that's our derivative of a constant rule. If the function is just a constant, then we automatically know that the derivative is 0. Easy. Okay, the constant multiple rule. So that says if f at x is some constant times g at x, where c is any constant, then f prime at x is just that constant multiplied by the derivative. So pretty easy, the constant just stays out front and then multiplies by the derivative of the power function. So the process of finding the derivative is called differentiation. So that's a word. So if they say to differentiate, that means to find the derivative. Find the derivative. Okay? So number 6 asks the question a bit differently then. So differentiate each of the following. So that means find the derivative of each of the following. So this one I'll kind of do out long, and then we'll see that we don't really have to do that. But our constant multiple rule says we can multiply 7 by the derivative of x squared, which we know is 2x, which would give us 14x. But most people can do that in one step, especially after they've had a little bit of practice there. F at x equals 12x to the 4/3. So f prime at x, we know it's going to be 12 times 4/3 x to the 4/3 minus 1, but subtracting 1 in a smart way would be to subtract 3/3 there. So f prime at x would be 16 x to the 1/3. And since the question came with a rational exponent, we can leave the question with a rational exponent. If it starts with a root, you want to finish your answer with a root in general. So here in C, so a question to ask yourself is this in the right format to find the derivative or to differentiate it? In C, I would say it's not, because it doesn't look like this power function y equals x to the n, and that's what we know how to differentiate. We even know how to do it with a constant up front, c x to the n. So we want to change this using our knowledge of exponent rules and rewrite it as 3x to the negative 1/2. And now it's written as a power function. Okay, so this is still y. These two are equivalent to each other. We've just changed how we wrote it. Now we're finding the derivative, so we can say y prime. So 3 times negative 1/2 is negative 3/2. X to the negative 1/2 minus 1. So if you want to write that out still, not quite comfortable doing them in your head, you'll end up getting negative 3/2 x to the negative 3/2. But then this started in root form, so we want to end off in root form. So we would have y prime equals negative 3/2 root of x cubed. If you remember back from grade 11 again, if you have a fractional exponent, the top number is the exponent and the bottom number is the root. And square root you don't need is understood to be there, so you don't have to write a little 2 in here. It's understood to be in there. Okay. Next. All right, D, y equals 1/4 x to the 4th is in the right format, so we're good. Y prime is going to be 4 times 1/4, which is 1, x to the 4 minus 1, so y prime is just going to be x cubed. G prime at t, so again, we don't just always have to use x, we can use different variables. So it's going to be 8 times negative 3/4 t to the negative 3/4 minus 4/4. So g prime at t is going to be negative 6 t to the negative 7/4. And again, we were given a rational exponent, so we can leave our answer in terms of a rational exponent as well. All right, so this one, f, not ready yet to differentiate, so I'm still just writing y here. I'm changing the form, so it'd be negative 2x to the, so it's going to be a negative exponent because we're bringing it up to the top. It's going to be rational, exponent on top, root on bottom. So negative 2x to the negative 2/3. So y prime is going to be negative 2/3 times negative 2, so that's 4/3. X to the negative 2/3 minus 3/3, so that's negative 5/3. And then we want to write it as a root, so y prime is going to be 4 over 3 third root of x to the 5th. All right. The sum rule. If f at x is equal to p to the x plus q to the x, then f prime at x would just be p prime at x plus q prime at x. So that's going to allow us to differentiate polynomial functions. So for example, if f at x is 7a here, f at x is 3x squared minus 5x. F prime at x, we can just take the derivative of this first one, which would be 6x, and then minus the derivative of 5x, which would be 1 times 5 is 5, x to the 0. So, and then you'd still want to add on, that's just 6x minus 5. You don't want to ever have x to the 0 in your answer, that would not be simplified. Okay, and then look at the next one, really long here, but we definitely would not have wanted to do that one from first principles, but now that we know the power rule, constant rule, and sum rule, it's actually very easy to differentiate or find the derivative of. So x to the 4th, 4x cubed, minus 3 times 5 is 15, x squared, plus 2 times 2 is 4x to the 1. This one would be minus 12x to the 0, which we don't need to show, plus the derivative of 3 is 0, which we also don't need to show. So f prime at x, we found it. All right, go up. We have y equals x to the 5th squared. So we might want to rewrite it first as y equals x squared over 25, which really we could think of as y equals 1/25 as our coefficient, x squared. And then we could find y prime. So that would be 2/25 x to the 1. Next one, g at t, not in the form of a power function right now, neither one. So we want to first rewrite g at t. So g at t we could write as 7t to the negative 4 minus 2t to the negative 1. And now we can find g prime at t. So negative 4 times 7 is negative 28t to the negative 5. And then negative 2 times negative 1 is positive 2t to the negative 2. Reduce the exponent by 1. And then these were written rationally, so that's how we should figure out how to answer the question. So it's going to be negative 28 over t to the 5th plus 2 over t squared. All right. This one, first of all, we have to rewrite h at x. And you could stop if you wanted and see if you could figure out how you would write it. Root 10 is just a constant, so we can't do anything with that. But we can write x over x to the 5th as x to the negative 5 minus 2. And now we can find h prime at x. This is really a 1. We'd have 1x to the 0, which is just 1. So this is going to be minus 5 root 10. 5 times root 10 is 5 root 10. X to the negative 6. And then the derivative of 2 is 0, so just minus 0. We don't need to show that. Simplify. We don't want a negative exponent if there wasn't one in the question. So we'd write it as 1 minus 5 root 10 over x to the 6th. This one, we would first want to distribute. Maybe even we would first, before we even distribute, we would want to write root r as r to the 1/2 and then distribute. So it's going to take us a while to make this one look appropriate for us to differentiate. So we have 2r to the 1/2 plus 3r to the, so when you multiply powers with the same base, you keep the base r and add the exponent. So it's 1/2 plus 1, but we could write 1 as 2 over 2, which would be a smart way to do it. So that's going to be 3r to the 3/2. So now finally it's ready to differentiate. I find the derivative of 1/2 times 2 is 1. So it's going to be 1r to the 1/2 minus 1, which is -1/2. Plus 3 times 3 over 2 is 9 over 2. R to the 3 over 2 minus 1, which would be r to the 1/2. And then we had roots in our question, so we have to have them in our answer. So that's going to be 1 over the root of r plus 9 root r over 2. Okay. And then moving on to G. Not in the right form. If you want, you could pause the video and see if you can predict the right form. But we want to move the t up, so its exponent's going to become -1, and the t squared up. Exponent will become -2. So that was just g at t written equivalently. Now we can find g prime at t. So derivative of a constant is 0. Don't need to show it. So we're moving on here. So it's -3t to the, reduce the exponent by 1, -2. -2 times -5 is +10, t to the -3. And then we want to write this rationally since that's how our question was written. So it's going to be -3 over t squared plus 10 over t cubed. All right, and then this one, again, not ready to differentiate. The first term is, but the second one isn't, so we want to rewrite it as 2. And then if we could bring the x up, and we know that that's a 1/2 exponent in the denominator, so it'll be a -1/2 exponent in the numerator. Y prime, take the derivative of this first one, 3x squared. Next one, -1/2 times -2 is +1. X to the -1/2 minus 1, but it's smart to write it as -2 over 2. There was a root in our question, so we should answer with a root. So plus 1 over the square root of x cubed. Okay, so that's going to be part 1. I'm going to stop, and then I'm going to go on. I don't know if it says low battery, so I don't know if it taped any of